So thanks everyone for our ACOM seminar today. I am happy to introduce Joshua Schwarz, or Shuka. Joshua or Shuka is good. Joshua is a research scientist working at NOAA. Over the past 15 years, he has been there, focusing mainly on black carbon measurements with single particle soot photometer. And we are happy to have you here, and come here.
Thanks, Ivan. You'll tell me if I'm talking too loudly, and tell me if you can hear me swallowing. No? Thank goodness for that. The small blessings. Well, thanks for having me. The first thing I'd like to say is I've changed the title a little bit. I know some people will be disappointed. So we started off with 1, 2, and 3 being absorption, nucleation, and fate. And I've just changed that nucleation to be lifetime because I realized that that's more interesting to me, and I think we can say a little bit more about it. The second thing I'd like to say is that there's some talks where you get a 3-course meal and there's a cherry on top of the sundae at the end because it's all completed and the whole story is done. What I'm going to be showing you is the mess that's in the kitchen. So we're going to look at quite a bit of data, but it's going to be very light on conclusion and baked food. It's all half-baked. But I find that also somewhat interesting, and hopefully it will help you guys become interested and give me some ideas about things we can do and ways we can look at this data. So the outline is pretty straightforward. I'm involved in FireX, AQ coming up, so the overarching theme that was somehow in the back of my head when I was putting this together was on fires, open burning, and the underlying theme, what I'm excited about with the data sets that we can achieve is addressing process level understanding. So I could give you some fully baked stories about conclusions without the process in there, but I didn't want to do that. So ABC 1, 2, 3, and a brief history of the future. The ABC is aerosol black carbon, what it is, why we're looking at it very briefly, and a little bit about how with the single particle soot photometer, the SP2. Then light absorption as the first topic of interest, and of course you can see why I have this picture of my daughter, because of her glasses, which absorb light, just like black carbon. And of course, black carbon isn't the only thing that's absorbing light. We're not actually measuring light absorption, but what we can do is by making our measurements of black carbon, we can at least constrain its contribution to light absorption. So I'll be talking about some of those things. Then lifetime. One of the big questions is, of course, the aging time scales, the lifetime of black carbon. It determines how much is in the atmosphere. And so it's a big question. And so here we can see some various model results as a function of with different aging timescales, different BC lifetimes, and that has a big effect on the amount that's out there. So I'll be focusing actually on what we can measure that helps constrain our understanding of the processes determining black carbon lifetime. And finally, my daughter was standing on snow, right? And so obviously there's going to be dry deposition to the snow, there's wet deposition in the snow, so that's why that picture connects to lifetime. And then finally, fate. And what this is a picture that I'll get into a little bit later, showing size distributions of black carbon in snow and its connection to our guesses at the light absorbing properties. But the fate is it's going to end up somewhere. We know when it ends up in snow, it has continued climate effects, and I'll be talking a little bit about our results in the lab that are relevant to that. Okay. The brief history of the future is just, there's a little bit of future coming up, and I'm going to make a guess at what's going to happen, but it's very brief, if we even get so far. All right, black carbon, what is it? So this is a great picture, unfortunately, from the Mendocino fire complex last year, and what you can see is flames and a lot of black smoke, and that black smoke is mostly black carbon, which is, its primary property of interest is the fact that it is light absorbing, strongly light absorbing. It comes from fires, it's refractory, so that means that it's going to survive high temperatures, it makes sense. And that means that it's not detectable with an AMS, which makes it hard to measure compared to many other species. It's not soluble, so we're not going to measure it with a liquid chromatography either. It's not very reactive, so eventually it's going to be a nice tracer, and that's an underlying theme, that we can use it to answer other questions about the atmosphere than just about black carbon. And it's really crazy shapes, so that means that it's very challenging to explore microscopically, the optics are complicated, everything about it is a little bit complicated. And it ages, it is not just like one material, like let's say some what would be a good corollary? Let's say like CO2. It's not like that at a lot. So it's very different to measure unambiguously. And to accentuate this morphology issue, what you're going to see here is a filter with a single black carbon particle on it, and it's going to rotate, and you'll see the complexity of that particle kind of coming out. And I make the argument that this is the most complicated primary aerosol type. And that's something that's really just to start a debate with somebody after this is all over. That will be fun. But I think I think I can back that up. Every flake is unique, and this is just one of the challenges that we're going to be facing when we try and measure these things and understand them. Which brings us to the question of why would we want to do that? What's our motivation? And as you can see from this figure, there's more than one. And the first one I'll talk about is climate impacts of black carbon. Now, about half of the black carbon is coming from open fires globally, and about half from fossil fuel. And it's affecting the atmosphere and climate specifically in a few different ways. So directly is the most easy way to understand. It absorbs energy from the sunlight. It heats the air locally. So that's ground zero. But then it has all sorts of other effects. It can act as a nucleus for condensation of ice crystals. It can provide a source for non-volatile species to condense on, including water, and so it can form some component of a CCN. And then these various effects can lead to semi-direct effects. So if you add some heating, let's say at the top of a cloud layer, and you're also dimming the surface and cooling it, maybe you're influencing cloud structure and making clouds disappear or appear, what have you. So these become more and more esoteric and hard to understand. Now, in the last, when I started this work, people were saying that black carbon was something like the second most important climate forcer after CO2. And in more recent years, this is revised down to maybe the third most important after CO2. But that very change tells you that there's a lot of uncertainty about what's going on. And this is just a quick picture in the quick graph in the style that we know from the IPCC, where there's a bunch of different ways that black carbon is influencing the atmosphere. So red is heating, blue is cooling, and it all boils down to one net forcing from black carbon with huge uncertainties associated with it. And for contrast, here's CO2, of course more important, smaller uncertainty. So I would argue that black carbon might be the third most important in terms of the actual heating, but it certainly is not the second most important in terms of complexity. Okay. There's other reasons why we're interested in measuring and looking at black carbon. It's more tightly correlated with health impacts than bulk 2.5 aerosol. It affects air quality. This is a picture from last year from Seattle when it was the worst air quality there was. I'm not really so interested in visibility myself. I wish I could say more about health, but can't really. We'll keep working on supporting the people who do that. And then it also has this utility as a tracer. So it's been demonstrated in snow and ice, and I'll be talking a little bit about that. So for me, the main point is climate, and then there's this nice usability feature of black carbon. Oh my God, I'm going so slowly. All right, people, it's going to pick up. So we're going to be using a single particle slit photometer, an instrument that I won't describe at all, except to say it gives you three different things. It tells you the black carbon, refractory black carbon mass of individual particles in a certain size range. It tells you whether that black carbon is internally mixed with anything else that's at an optically significant level, and it gives you a measure of the optical size of the total particle. Individual particles, very sensitive. Great, wonderful instrument. Thank God that whoever it was thought of it. This was from Ball Aerospace initially and then brought up by DMT. Here's a graph showing you that it's like magic. The vertical axis is some signal that we measure in the instrument, and the horizontal axis is the mass of the black carbon content of individual particles that were mass selected, and you can see there's this magical linear relationship. So when a particle comes through, we can know the mass, the black carbon mass content of that particle. It's independent of all that crazy morphology that I was showing you. It's independent of whether there's other materials mixed in. So that's our magical tool that's going to give us some insights, hopefully, into what's going on in the atmosphere. Is this time correct that I have here? Does anyone know what time it is? I don't have my cell phone. All right, well, okay, that's better. We can slow down a little bit, but barely. So stay with me. All right, so I'll just say the sp2 has a laser, particles go through the laser's infrared, most particles just scatter light. If there's black carbon, it absorbs enough energy that that black carbon heats up to vaporization. It's refractory, of course, so that's pretty hot, 4,000 Kelvin, and at that temperature it glows with incandescent light, thermal emissions, black body radiation, just like an old-fashioned light bulb, and that's this vertical axis that I'm describing here. Okay, so there's the physical principle. But let me mention some of the limitations of the instrument. So it doesn't measure very small black carbon very well, and it becomes a struggle to measure bigger black carbon. So this is a series of mass size distributions plotted on some size scale that you can't see. It isn't really actually important. And the point is that this bottom side is set by the limitations of the instrumental technique. But what you can see is we're still getting most of the distribution in the log normal here, right? So this is where we typically see black carbon in the atmosphere, and this instrument, the magical instrument, happens to work right there. It doesn't work at smaller sizes, so here we're looking at number instead of mass, and in number you can see, oh, we're missing a lot, depending on the situation. We can miss huge amounts. If you sit right behind the right kind of engine, you see no black carbon at all. My 1992 Honda Civic, for example. But we know there's some black carbon there. So I'm only going to talk about black carbon number very rarely. There will be some mention to it. But for mass, we're doing pretty well. Now, at our labs in Boulder, we have 4 sp2s that you can see circled here. So beware. Everything looks like a nail. So we can start on that science-y type questions by hitting the nail of absorption. Now, all I said was that black carbon is contributing strongly to absorption, and the way that it contributes turns out to be very complicated, right? So I mentioned morphology. That morphology affects absorption. So here we see a black carbon particle stuck on top of something else, and this other material can influence the way that the light is interacting with the black carbon component and can change its absorption. Over here, what we see is a fluffy black carbon particle, such as is emitted by fairly efficient burning. And then if you take that same particle, you cloud process it, you coat it with something else, it can collapse into this shape. Now that has a really big influence on the scattering of the black carbon component, but it also influences the absorption. Okay. The sp2 isn't going to tell us the difference between those two because I just told you that it's only telling us about the amount of black carbon independent of morphology. But it will give us some information about the difference between this and this because we know the scattering from the whole particle. So when there's a lot of additional material, we can constrain that. I'm going to be showing you some results of coating thickness, which is using a model where the black carbon is a perfect little sphere, concentrically coated with a non-absorbing material with an assumed index of refraction, and I'm using me theory to turn a crank and change the amount of light scattering that I've measured and the black carbon mass content that the instrument has provided into a coating thickness to give us some more insight into what's going on in these processes. All right, so I mentioned morphology, I mentioned internal mixtures. Size of black carbon also is going to influence its absorption. And the best way we can guess at that is by looking at me theory. So this black curve here is showing the absorption per unit mass of black carbon as a function of the black carbon size. And so what you can see is, oh, here, there's a lot of absorption per unit mass at this particular size. That's due to some me resonance. And as you go to larger sizes, you start switching to a macroscopic phase where particles are absorbing by their surface area instead of by their mass. Down here, we're in some volume regime where the whole volume of the particle absorbs. Here's 2 different size distributions measured in the lab. And what you can see is they're different. And so that's going to result in some implications for absorption. This is using me theory, so it isn't accurate. The black carbon has these nodules, but we haven't figured out a way to measure this in a real way. So this is what I'm using as a proxy to try and estimate the possible influences of size. Now, over the size range that we've seen in the ambient, it looks like something like a factor of 2 in absorption. So that's the level that we're talking about. Another thing we can look at with sp2 is the internal mixing. And here you can see a graph from Chris Kappa's very recent paper showing an absorption enhancement. So the increased absorption factor for the black carbon component when you add internally mixed material, and that's plotted against the radius of the coated particle compared to just the core, the black carbon radius, assuming these spherical particle sizes. What you can see is there's a lot of variability. It doesn't all agree. So there's a lot of a question here, but this scale is going up to 3. We can say maybe we're looking at another factor of 2 from the effects of internal mixing on the absorption from the black carbon. If we put those two things together, we're talking about a factor of 4, and we should certainly be taking a look at this. Now, on the one hand, I try and make you think that things are complicated because, man, they are. On the other hand, I try and make you think that SB2 is at least giving us some simple answers, and you'll see that that isn't quite the answer yet. One of the additional reasons why things are complicated is because fires are complicated. So here's a picture of a beautiful fire. Lots of black smoke, lots and lots of white smoke. Who knows what's going on? Who knows what's controlling that? Who knows how these things mix? What are all of the parameters that are influencing what's coming out? Lots and lots of them. And so this is what we're going to be facing later this summer, and we're going to be struggling to make some connections between what we can observe and the underlying processes that are driving these things, and making connections between, let's say, fire radiative power and the efficiency with which the fuel is burning, and the state of the materials that are coming out. So some progress has been made, and some of this was in the laboratory at the fire lab. So I'm showing you here. So just a little picture. So we're talking about tiny little itsy bitsy miniature wildfires in the laboratory with a bunch of different fuels. So this was work from 2016 that Carol Lamb, one of the scientists in the group, has done most of the analysis on. So there's 108 fires with different fuels, sometimes repeated, lots of instruments, lots of people involved, and already some results that hopefully we can apply to understanding black carbon a little bit better. But right now I'm telling you more about just what we're observing, what we're starting to get a grasp of. So the two things I just discussed was size of the black carbon and the internal mixing with black carbon. So here's a graph showing the mass median diameter, so essentially the center of those log normal distributions of black carbon for different fuel types. And what you can see is there's a lot of scatter. This is for different components of trees. And if you just focus on a narrow set of fuels, what you can see is the size can vary quite widely. Oops, I should say. These are ambient measurements made in the free troposphere during DC3 in 2012. And you can see that it's pretty much the same range that we're seeing over most of it, except maybe things get a little bit smaller in the laboratory. And that might be a reflection of the fact that we're not getting to see fires from aircraft until they've aged quite a bit. But we wouldn't have enough data really to say at this point. Still, it's something to keep an eye on. So the point here is one type of fuel, you repeat it, and you get very different results. Okay, so all of the complexity, we don't have a handle yet on all of the parameters that are necessary. We haven't made the connection to what we need to be looking in order to keep track of what of the processes that might be determining black carbon's optical properties and absorption. Let's take a look at that second dimension, the internal mixtures. So now the vertical axis is the coating thickness using that simple model. And you can see huge variability again, right? So in the blue is a range that was seen for fires in 2013. And then in blue was the average of that. This dark blue is the average. And then this Pagami Creek fire was a very high UTLS transported fire plume that was going across the Atlantic to Europe. So kind of falling in that range. But we see very, very, very much different black carbon in the fire lab. So these types of coating thicknesses are what we expect to see with urban emissions. That's the only time we ever see anything even approaching that in the ambient, fresh urban emissions. So what we might think is that if we only look at efficiently burned flames, we'll get very thin coatings. Now in the urban environments, we also have smaller black carbon. So we might expect that to be associated with small black carbon, and only for inefficient flames will we get thick coatings and big black carbon. But that's not exactly what happens. So here we have a graph of that size against the amount of coating on the black carbon. colored by 1 minus MC. So black is a very efficient flame, yellow is a very inefficient flame, and here, all of these guys with very thin coatings, you can see they do have fairly efficient flames, except for that one. So I'll say we're half right. When you look at this, they're lining up like this. So that's why I say I'm half right. But when you look in this dimension, there's still a big variety in size. They aren't all small. So I'm half wrong. So what we've done is we've been able to make some observations. They're obviously connected to the processes, but we haven't made the connection to how to predict these properties, how to control them, and so on. But what we can also do is we can track them through time. So here's one last graph for you. That one last graph from the fire lab, in which I'm showing two different curves. The black is fairly fresh smoke that was sucked into a barrel, and then the red is after some aging in the barrel. And the horizontal axis is the mass of the black carbon core. So we're exploring particles with just a little bit of black carbon, more and more and more. And then the vertical is coating thickness on the upper graph, okay, to see how these are trending across the black carbon population. And over here, we're looking at the ratio of coating volume to core volume. So when we first suck this smoke into the barrel, what we see is there's no dependence on this ratio on the black carbon mass, which frankly I struggled to understand. It's like magic that the amount of material mixed onto the particle is related to the mass of that particle, not its surface area or anything else. But if you wait for a while, that changes and you get this trend. That makes some sense because coagulation processes with the underlying aerosol you'd expect to be driven by surface area, and these bigger particles are going to have more surface area. So on the one hand, we get a glimpse at some of the process that's going on in the flame. It's kind of interesting to try and understand. On the other hand, we're getting information about this coagulation process. So that's very interesting, and that gives you a hint of how we might proceed with trying to understand these things in the atmosphere. And so to that end, I'm just showing you a quick result from Seekers, from Anne Paring's paper, where she was tracking, in a Lagrangian sense, smoke from the rim fire, the big fire in California, where this is coating thickness and that's age according to high split. And what you see is this trend of increasing coating thickness. Now, on the one hand, that looks like a very simple graph, but on the other hand, what that is the end of a whole bunch of different processes all mixed together. And we're getting concrete information about what the end result of those processes are. So we're talking about aerosol phase partitioning, we're talking about coagulation, secondary production, all of those things are combining, and black carbon is an inert tracer that we're using to track those processes. So that's kind of the thrust of what this whole talk is about. How are we getting at those constraints on the underlying processes? But I can tell you're starting to fade, so let's switch to lifetime. I love being able to use quotes from Einstein. I have a little patience with scientists who take a board of wood, look for its thinnest part, and drill a great number of holes where drilling is easy. And so the only response that I have, and so, I'll just say that I have, is to look at the data set from HIPPO and ATOM that occurred from 2009 to 2018, to last year, where planes flew around the Pacific and the Atlantic, constantly going up and down and measuring black carbon all along the way. And so I asked Joe Kadich, who was involved in ATOM strongly, to give me a graph to show you guys about the mass mixing ratio vertically resolved from these measurements. And what you can see in blue and red are those two different data sets over nearly 9 years apart, agreeing very well over the entire Pacific basin. And then what you see in black is the AeroCom suite of global models. And what you can clearly make out on this log graph is a big discrepancy. And that discrepancy has been linked quite clearly to adequate removal in the models. Okay? And a case in point is that Pengfei Yu has taken one model and is showing us some results of changing the way that the model deals with removal of black carbon. So here what you see is, in green and red is the ATOM and HIPPO. They're not agreeing here because he's taken just a subset of data, so that's why you don't see that great agreement. AeroCom in purple, and then the Karma model in black initially, and then after he changed removal. issues. And what I wanted to do was just point out one cogent sentence from his abstract, namely that you fail to consider secondary activation and you overestimate black carbon's radiative forcing by a factor of 2. So radiative forcing, that's really being driven by its lifetime. If the model leaves it in, it keeps absorbing, it keeps influencing climate. And so if we can add some handles on, well, why is this process allowing the model to do better than that process, then I think we'll be making strides forward. The way we attempted to do this was, of course, by asking more and more questions of the atmosphere. So I'm going to be showing you some results using 2 SP2s, where one was humidified and the other was flown dry. Okay, so what I'll be giving you is information just about the black carbon containing population, with and without additional aerosol phase water incorporated into them. So this kind of summarizes what's going on. Here's some measure of scattering from particles containing black carbon. And here I'm showing you histograms where there's nothing in there but black carbon. And wet and dry, you see the same thing. And that's because black carbon alone does not take up water. But in the atmosphere, what you see is a shift between these 2 histograms. In red is the dry case. And then in the blue, we're seeing that water has become associated with some particles and therefore shift the scattering to larger amounts. Now what I'll be presenting is something I'm calling an F factor. It's just a factor between the wet scattering and the dry scattering. So high F factor means, oh, a lot of water went onto that population. A low F factor means no water went onto the humidified population. And this is very much a corollary to F of RH, namely the ratio of scattering of total aerosol between wet and dry conditions. All right, so we flew this in Seekers and DC-3, but we kept getting better and better at it. So I'm going to be showing you results from the Chorus mission, which was 2016 on the DC-8 over Korea, where there was a whole lot of other instrumentation on the plane that we'll be using as well. So here, this F factor that I just described as a function of black carbon coating thickness, this is for 1 minute data throughout that entire mission, colored by acetonitrile from Armin Vistaller's instrument. And what you can see is high acetonitrile is biomass burning. And here's a big thumb of stuff with very thick coatings, which is not too surprising because that's what we tend to see from biomass burning, and not so much water uptake. No one really thinks biomass burning is super high water uptake. It's not like a nitrate or sulfate. But notice also that you see some high acetonitrile points in this whole blob here. Okay. So that's the first observation, and the question is, what does that mean? And I don't know what the answer is. So we keep looking at additional parameters. First, let's look at the relationship between the black carbon population water uptake and that of the bulk aerosol. So here's the black carbon water uptake, and then here's that F of RH that I mentioned as a corollary for total aerosol. You see a blurb of stuff that's pretty messy, but something like a trend. The black is 1-to-1, so we aren't completely off of that. And so the whole picture you might be tempted to say, oh, for black carbon it's probably just the same as everything else. And in fact, that's a little bit true, but it isn't 100% true, and that's what makes this interesting. So what we can do is we color this now by coating thickness and try and understand what's going on. So now when you color it by coating thickness, what you see is, oh, here's a population of black carbon. That's probably our biomass burning, right? Because that was what was so thick before. Remember, it stuck out. And this is lying above the 1-to-1 curve. So what is that telling us? It's telling us that the black carbon population compared to the rest of the population is relatively more water active, right? Which is a little bit surprising. I found that surprising. Okay. If we look at these guys that are low down here, you can see that there's these big red points. Those have very low coating thicknesses. And now that makes a little bit more sense because if there's no coating on black carbon, the black carbon isn't going to be water active at all, so it falls below the 1-to-1 curve because that particular population isn't reflecting the general makeup of the rest of the population. But it isn't quite so clear because remember I had pointed out those kind of intermediate biomass burning particles, which weren't so thickly coated. And here what you can see is those are falling right on the 1-to-1 curve. Okay? So this looks like very different behavior. And what this is means, I think, is that we're probably looking at the difference between aerosols where the black carbon population is still distinct from the background, whether it's because of different sources, and a population where everything perhaps has been cloud processed or so aged that it all becomes essentially uniform. And the coatings are so thick on the black carbon that the behavior of those particles is pretty much the same as everything else. Once again, the point is that all of these processes are boiling down to something we can measure with a single particle photometer, and at the end of the day, we've got a constraint on that net action. Now, where the net action really is important is in terms of CCN, right? That's where the question of what's getting removed is coming up, at least through that mechanism of condensation scavenging. So here what I'm showing is black carbon number. This is the only place where I talk about number. It's just what the sp2 saw for number concentration. And here's CCN at 6% supersaturation. So that's a pretty high supersaturation, so it maybe is a proxy more for just total aerosol concentration above 80 nanometers or something like that. And I've colored it by coating thickness. And so it's the same kind of story. We've got some relationship where, of course, black carbon is in most of the particles, so we have a 1 to 10 line here instead of 1 to 1. It's only a small fraction. But we can take a look at this and try and understand what's going on. When the black carbon is thickly coated, purple colors up here, tends to lie above this line. It kind of makes sense because you're going to have more CCN activity if you're a bigger particle with thick coatings. So that makes some sense. Here we've got our little red guys. It's just black carbon. It's less likely to be involved. Of course, what's dominating this is bulk aerosol, right? And this is just black carbon, a tiny component. But that's how I've been thinking about it and trying to understand what's going on. All right. Coloring it by the F factor, I was rather surprised by this, okay? So high F factor means the black carbon population is picking up a lot of water. I would have said, oh, they're more likely to be CCN. But it turns out they're a smaller fraction of the total CCN. And it turns out this makes a whole lot of sense. What that means is, you're in an air mass where there's a lot of water-active type materials. Let's say you come out of an urban area with a lot of sulfate. Some sulfate falls onto black carbon. Great, you're going to have more water-active black carbon, but you're going to have a huge number of non-black carbon water-active species. So I think that that's what's being reflected here, and it's kind of giving me a sense about this complicated interaction of black carbon population with the rest of the population, right? We're talking about a trace here that's normally like 1 or 2% of the total aerosol population. But understanding how it can be used as a tracer of the larger air mass and the changes to the larger air mass is quite interesting. Now, Anne Perring's paper, which I showed you a result from before, coating thickness, she also was tracking with this 2sp2's water uptake by the black carbon particles. She was showing it as kappa instead of F factor, right? So kind of some size thing was taken away. High kappa is more water active. And the point is that what you're seeing is, in blue, is the result from the sp2 with aging. And so at the end of the aging, you have more water-active black carbon. You also know what's going on. And so this is, again, at the end of a line of a whole bunch of processes. Oxidation reactions, all of the phase transitions, all of that is boiling down. And what you get is, you get a population that's more water-active. Now, if you didn't have this black carbon data, would you really know that? You might just say, oh, well, there's more particles that are larger because of the condensation of secondary species. And that would be something different, okay? So, I'm not saying you can't make a measurement with an AMS about the O to C ratio, but what I am saying is this is another way to get that information kind of at the bottom of the line. I'm really running out of time. No, I'm doing pretty well. We're doing pretty well together. And guess what? Fate. Okay, so the fires burn and the smoke goes up and it gets transported and stuff gets removed, and some of the stuff gets removed into snow and snow areas, okay? And so cryospheric, meaning in the snow or ice, black carbon is relevant to the removal rates because if there's a lot in the snow, it must have come from somewhere through one or another removal mechanism. It changes the color of the snow essentially, changing how quickly that snow ages. That turns out to be the main thing. It's not that you take white snow and you put a tiny bit of black carbon and now it's gray and melts really quickly. It's rather that you put in a tiny bit of black carbon and now the snow, instead of remaining super light and fluffy for 2 days, it stays super light and fluffy for like 1.7 days. And when it's not super light and fluffy, it's not absorbing so much. So therefore it becomes less reflective, and now we start getting climate impacts from the snow. But the reason I'm talking about it today is more about process level understanding, and what I'm going to try and show you is that we can see changes in black carbon size distribution between the atmosphere and what we see in the snow that I think have to be connected to both the processes on the ground and in the air. This is a really nice result, which was the first result showing direct black carbon measurements in snow with an SP2, and this is concentrations from an ice core. So you can see it going back in time to 1800 with some peak starting at the Industrial Revolution, apparently. So kind of nice as a demonstration of a tracer, and I call it the upside down tape recorder because I was thinking of that tape recorder of water vapor at the tropics, but this is going down. Really very different. I shouldn't have done that at all. So process level understanding. So one point that I want to revisit was the range of size distributions that we see in the atmosphere. So I had showed you this graph before, just saying we were covering most of the mass range. But what you can see is also, this is an urban result, small black carbon. This is an open burning result, larger black carbon. And in the remote, here's 3 results from HIPPO over a couple different years over the Pacific in the remote, where you can see things are really very remarkably stable. So this is what I think of as a typical, and I'm going to be showing you this remote as a typical size distribution in the air. But I also wanted to point out that there have been instances where we see very large black carbon in a larger mode that's harder to distinguish the SP2 in the air. So this is a result from China. I think that might have been tire burning, but we'll call it tire burning is illegal in that part of China because of the pollution, but it occurred at 2 a.m. So we'll just call it open burning. And the point is there can be some large particles in the atmosphere, but generally we just never see that stuff. All right, and what I'll be showing you is results of looking at black carbon size distributions in snow from a variety of places. Carl Schmidt, NCAR, great guy, likes to mountain climb and climb mountains in Peru. So we'll get some snow samples from there. Sarah Doherty, great scientist who connects snow all over the place, and she gave me lots of samples from North America that I melted and put into SP2. And also Susan Kaspari from, I think, Central Washington University gave me some ice core samples where there's a black carbon layer from biomass burning. That's kind of interesting. And then Jack Dibb nicely got me some samples from Greenland. Well, maybe I was helping him, and we got to measure some samples from Greenland to double check their results. That was a wider effort, but frankly, I can't remember the name of the main contact person there. So Greenland, both hemispheres, let's see what we see. So what I'm showing you is the size distribution in the remote and the atmosphere, right? So let's think of that just as a starting point for what's in the air. Snow falls, it collects stuff, and this is what we see in the atmosphere. Now this is from Greenland. The Greenland snow is reasonably clean. It's kind of hard to get statistics out here, but what you can see is there's kind of this gentle shift into regions that, while we really never see a mass median diameter at that size in the atmosphere, except for a plume of this, a plume of that, you just don't see it generally. So that's interesting. And now we'll take a step back and look at the North American results. I also took snow samples right outside of the lab in Boulder. So the snow would fall. I would come in early before the sun hit it. I would take the snow, melt it, and measure it. And this is what I got. Now what this is very consistent with what we'd expect in the air here in this urban area that's much smaller than what we see in the remote, right? That's what I showed you before. But we also see some giant black carbon particles at a much higher frequency than we would expect. So that's interesting to note. Over all of North America, what we're seeing is something very similar to the remote, but also these very large particles. So what can it mean? Let's take a trip to South America. Pretty, huh? Pisco. So Pisco is, somehow Carl got up here. He got up there and he took samples and he managed to get them back. So it's remote and it's clean. And then he also climbed Via Narahu, which is not so remote. It's like downwind from some hugely populous, dirty city. And he also got up there with a crew of scientists and samplers. And the results are really quite striking in my opinion. So here's our remote. And now what you see is an extremely dramatic shift of the size of the black carbon to larger sizes and also with large particles. This this purple guy is falling off there because Pisco had such clean snow. All right, so you're seeing the theme already develop. And now one last one, this biomass burning. So here you see a main peak. Again, it's kind of consistent with where we might expect the aerosol phase stuff that's come out of the fire to be, but then a huge number, huge contribution in mass space of these large particles. Now, you remember I showed you some me-theory curve of the mass absorption cross-section as a function of size. So here, it probably would be more than a 50% impact if we could believe that. All right, so what's the bottom line? The bottom line is there's a huge range of sizes that we're seeing in the snow. And there's sizes that we just don't see in the atmosphere, right? And those sizes are occurring even in very fresh snow where nothing has possibly happened to the snow. It fell out of the sky and that's it. So some process in the atmosphere is driving these large particles. What could that process be? Well, here I'm showing you size distributions where I took black carbon in the laboratory, I put it in some water, and then I froze it and thawed it and measured it, and froze it and thawed it and measured it. And what you see is we increase the number of freeze-thaw cycles. The black is showing, I think the black is showing, oh, it's 3 different concentrations I did it at. So this is what we're starting with, no cycle, something that looks very much like the atmospheric situation. And you'll see there's nothing past 1. And then we go up in cycles and we start seeing these giant particles. So the ice is forming, it's excluding the impurities get packed together and you build bigger black carbon particles. And I would argue that we have evidence that this has occurred in the atmosphere. So I think this is happening in the clouds, and it's quite intriguing to think about what kind of a cloud process could get you to collect aerosol as a liquid droplet and then freeze and generate these large sizes. We're also seeing this kind of slow step over of sizes in the atmosphere, and that's probably a size-dependent removal effect. But we will try and better constrain these things with additional measurements, with understanding the variety of size distributions from black carbon in snow over larger areas in different populations. Different geographic regions and so on. But you can see how this is giving us some information at the end of the line of what happened to the black carbon. Now, these freeze-thaw cycles, they can happen on the ground too, right? So the reason I'm saying that happened in the atmosphere is because of that snow that fell, and then before anything could happen to it, I measured it, where we already saw these big particles. But once the snow has fallen, it still can freeze and thaw. That happens quite often, actually. And so that can affect the size distribution of the black carbon that's sitting in the snow, and therefore its interaction with the ice, as I was describing before. So here's just showing in this size range that me curve of absorption cross-section as a function of size, where you can see, wow, there's a lot of black carbon here that if we just believe me theory isn't doing a whole lot. Okay, so that brings us to the end of science and the start of the future. But as we all know, the future starts with the past, and so therefore I will quickly summarize just the main points I want to take away. So absorption, I told you that absorption depends on black carbon's microphysical state, and I didn't actually show you any proof, right? I just told you that. Oh, the morphology does it, this does it, that does it. That's been done in a lot of work up till now, but I didn't show any of it. But what I did show you is that somehow we're making measurements that are tracking the processes affecting those things that are important for absorption, the size and the internal mixing. Okay, for lifetime, I showed you a demonstration that, that the Hippo and ATOM models are different than the old models that haven't been improved, and so they're constraining models. So we can look at just the black carbon concentration all over the world and make Einstein happy that we're not lazy. I call this a top-down view. But what we can also do is take a deeper look at the underlying microphysics and try and understand those processes a bit better. We've been doing that by looking at this water uptake and trying to untangle what's happening. And then finally, post-deposition, black carbon continues to have a role. In fact, people collected out of sediments at lake bottoms, so there's much more going on than what I described here. We've been looking at black carbon in snow because of the obvious climate effects. And I'm pretty convinced that the size distributions that we're seeing are reflecting really atmospheric cloud process level occurrences. So that's what we just were, the outlook. These are just a whole list of efforts, things that we're interested in looking at further, a lot of contributing to model improvements. That's always got to stay big. Fires are coming up as part of FireXAQ, starting at the end of July, the science, with a whole bunch of aircraft, mobile labs, ground stations, satellite involvement. So that's very exciting. And of course, the processing will take a lot of time and digesting all of that information, but the wider the community, the easier it will be. And monsoon influences, so I just wanted to have another quick slide up here. Next year, there's this wonderful, terrific, fantastic ACLIP model mission, Asian Summer Monsoon Chemistry and Climate Impact Project, where a lot of aerosol is getting pumped up in the atmosphere from this high pollution region. And we're very hopeful that the measurements with the SP2 can help contribute to defining that end of the line state so that we can get better understanding about, well, first order is how much black carbon is getting up there, and then also what are the properties of the black carbon? What does that tell us about what's going on, what survived, is it all secondary production, et cetera, et cetera. And so with that, I would like to thank the many people who have contributed to all the information you were seeing here, and specifically from the NOAA Black Carbon Group, Joe Kadich was involved with the snow measurements and also flew most of ATOM. And so that he's been contributing very strongly in that dimension. And Kara Lamb has been a wonderful collaborator, really sharp on the analysis. She was in Fire Lab, and most of the Fire Lab results are thanks to her, and also was a big part of supporting Course AQ and making sure that that happened. Ann Paring, by the way, also had a big footprint in this talk. She's moved on to Colgate, but is still in touch, and I'm sure would love to hear from all of you. So Ryan was a big part in the earlier days. Pilots and crew are always thanked. Sarah Doherty, Susan Kasperi, Alia Khan, and Carl Schmidt really contributed snow. If they hadn't given us snow, we wouldn't have been able to measure it. I also like to point out the AeroClim initiative that's been so wonderful for accepting the work and responding to it. And so thank you for your kind attention. And if there's any questions or comments, like that guy's.
You expressed surprise that the initial coding was proportional to the mass of the black carbon rather than surface area. Given that these are fractals, isn't it possible that the surface area is proportional to the mass?
Yeah, that's something that we aren't really sure about, because by the time that we get to see the black carbon, under the cases where there's a lot of coding, it's already collapsed. So when that happens in the process, it's very hard for us to know. So that's an excellent point. Thanks for pointing it out to me. But absolutely, if it's hugely fractal, then the surface area would scale exactly with the mass. Yeah. And I'll still go back to that. There we go. You know, I have to admit that I hadn't seen this slide in a long time before I was preparing this talk, and I had misremembered it as, instead of the ratio, I thought this was the absolute coding volume. And so when I was thinking about it, I was thinking of a fixed volume independent of the black carbon mass, and then I realized what was going on, and I had to check to see what I had actually calculated, but thanks for pointing that out.
Hey, Shuker, on the IPCC diagram, is that total impact along the bottom based on a bunch of models that are overestimating HIPPO and ATOM by a factor of 2?
Oh, Brits.
And if it is, where do you think it's going to go?
I've lost the cursor. Here we go. Let me just do this real quick. So that wasn't actually IPCC, it was IPC style. Sorry for not being clear. This is Bond et al. 2013, so bounding the role of black carbon in the atmosphere. And your question was whether this result was using the AeroClim models and off by a large factor. So I happen to be a co-author on that and got to hear a bit about the sausage making effort. Basically, that AeroClim was part of the basis for the bonded-all number, but it had been modified in order to account for known discrepancies in aerosol optical depth and AEOD, absorption optical depth, from the sun photometer network. So because it did take HIPPO into account, and it made a 15% correction to the Aerocom suite, remember that in HIPPO, in the remote, we were seeing these huge discrepancies, but it was only after there wasn't a whole lot of black carbon left in the atmosphere. If you look at the ATOM results, Aerocom is underestimating black carbon still in those source regions. So it's a complicated play between different things going on. But this number was made quite high, not because of Aerocom, but because of those sun photometer network results in various regions, most notably off the coast of Africa. It turns out that there had been some component of coarse mode absorption that had been attributed to black carbon, and that's what drove a lot of this. But in discussion with reviewers, there was no explanation at that point about what was going on. And so I think their initial estimate had been more like 0.7 watts per meter squared. And this is like almost 1.1. But that's what drove most of this high number. If you look into literature, you see some values down at 0.2 and so on. But it kind of boils out at the near methane level around 0.5, 0.6, that ballpark. But as you can see, the main point is the uncertainties, I think.
Hey, I have a question about, for those of us less familiar with CHORUS, 300, I'm guessing it's PPT acetonitrile, isn't significantly high, so it doesn't look like you guys sampled really strong fires. But do you have it constrained where a lot of that fire influence was coming from? Was it kind of local, a lot of local sources, or was it a long-range transport?
My memory is that most of it came from Mongolian fires that had been transported kind of down to Korea.
So possibly fairly aged fire.
Yep. Yeah, thanks for pointing that out, and I'm very excited that in FireXAQ, you'll be right there helping us make these plots better.
Can't wait.
Yeah. Oh.
On this 1 micron side, where you're talking about this Aerocom,
you see that downwind of fires where there's size distribution measurements in the atmosphere. You even see it in the boundary layer at the extinction event of the dinosaurs. And usually what people think it is just a lot of high winds there that are blowing stuff off the ground. It's got a lot of charcoal in it.
Yep.
Did you have some other theory for its formation?
So in general, we agree that there's huge amounts of aerosol over much wider ranges than we typically see black carbon. But this is specifically black carbon. And so the processes that lead to a particle that's, let's say, 3 or 4 microns, a mineral dust particle that's 3 or 4 microns, isn't going to lead to black carbon that's that size. So the source of the black carbon is always going to be combustion. And, as I was showing from those open fire size distributions, that's falling in a size range that's kind of over here, right? So if we are willing to accept that this is that same material moved over, then I don't think there's any question about this being something like fly ash or a whole different species. The fact that I was able to reproduce this with really just black carbon and nothing else, I think is a strong support for that. So this isn't the total aerosol population, and it probably isn't these kind of larger particles getting knocked down into these sizes, I don't think.
I think the stuff that you often see in the atmosphere is actually got black carbon in it, and it's often charcoal. They get a lot of stuff that isn't, this charcoal, and it gets blown up in the wind instead of forming at the flame front, but it's still got black carbon in it, so it's...
I see. Yeah, so I'm actually quite excited about some of these things in FireXAQ. We're also going to have cloud probes that will make it easier to see some large particles. There was some work done by Konrad Kandler in Germany where they had a filter at the front of the Falcon, and they were looking at really giant particles coming out of the fires, likely due to more of those types of processes. So I agree that that's an issue. I don't think that that's what we're looking at here. I don't think we're looking at fly ash or large particles that have been lifted up somehow by wind. These results Greenland, for example, the transport of those large mode particles would be very, very long indeed. And if it was really kind of massive, it would be hard to imagine them making that trip with high efficiency. So I still think that this is something that's formed from combustion that we're looking at, where we're talking about the smoke from the fire, and depending on the fire, it's true that can be over some large range, but typically we see a smaller range. And then I think it's the processes that are moving this over. Once particles get too big, it's very hard for us to sample them. But I've tried a bunch of different black carbons in the laboratory, and they do have some different characteristics. So there might be a chance in a situation like Fire XAQ where we know this might be an issue to try and distinguish those things. But for this, I think it's really just this combustion black carbon. An assumption.
Can you say a little bit about the experiments that you did?
Which ones?
The one you stuck particles in water?
Oh, yes. A brilliant maneuver. Actually, I have an idea how to do this differently. So what I did was I took 3 bottles of water. What I did was I took black carbon powder of a certain type that looks very much like what we see in the atmosphere. I mixed it with water and I let it sit for a weekend. And then I sucked out the water that was at the top that was still black. So big stuff had fallen out. Then what I did was I took some of that liquid and I put it in a beaker. I knew how much. I evaporated it and I measured the amount of mass change of the beaker. So I knew the amount of black carbon in that sample, okay? So I have a gravimetric standard of a black carbon standard that happens to be in the size range that we typically see in the atmosphere. Then I made up 3 mixes of that of different levels of concentration. And these levels are, wow, it's way worse than China. Wow, it's as bad as China gets. And wow, it's 10 times worse than we see here in Boulder in terms of the concentrations in snow. I took those guys, I put them in, and I turned them into an aerosol and measured them with sp2, and I saw these size distributions. The size distribution is pretty much independent of the concentration because we've got a good instrument and a good technique. Then I froze it and I thawed it, and the size distributions had shifted, right? I froze it and thawed again, I froze it and thawed again, and I was able to develop these very large particles and shift the whole size distribution over.
When you attribute this to your best guess.
Okay, so my best guess is, imagine water with black carbon floating around in it, and you initiate ice somewhere at some inhomogeneity of the glass surface. The new idea, by the way, is that I can freeze ice onto a surface and make like an ice cup and then do it in an ice cup. So an ice crystal starts growing, right? Because the heterogeneous ice growth is going to be much easier than initiating homogeneous stuff. And the ice is, as it's forming, it's excluding impurities. This is something that's well known. So if you want to make very nice cocktail ice, what you do is you take a big thing of water and you freeze it from above. And the initial ice is beautiful clear because there's no impurities. And then you get to the bottom and all the impurities freeze and you get the horrible, ugly ice that you don't put in your drink. This was distilled water.
But it still had impurities in it.
It had the impurities that I put into it, namely black carbon. Yep. Yeah. And so that was the mechanism. Actually, Rushan Gao proposed that because I went to him and I said, "What's happening?" And he said, "Well, it's probably the ice excluding the black carbon. It gets smushed together." And I thought, "Oh, brilliant! Explains it all." So does that make sense? If the ice is excluding those particles, then they get confined to smaller and smaller volumes. And then when the ice finishes freezing, it's all kind of smushed together.
They agglomerate.
They're what?
Agglomerate.
Yep, they're agglomerates. I believe that. And that's what I think is also happening in the atmosphere.
Any more
Wow,
questions?
the questions, comments. It's very flattering.
A couple of quick questions. Any relationship to tar balls in these large?
Yeah, so that's a very interesting question. And tar balls is one of the things we're very interested in studying. So this is a non-black carbon, light-absorbing substance, probably coming a lot from fires. So in the past, a year and a half ago, I would have said, oh no, it isn't that because tar balls don't absorb at the wavelength of the sp2 very efficiently, so they won't heat up, nothing will happen. Actually, I still believe that's true. So in terms of the measurement, I don't think we're measuring black carbon. That said, there's been recently a paper from Art Sedlacek at DOE where he nebulized negrozine, so an extremely highly absorbing kind of complex organonitrate ink, and what he saw was that with the sp2 you could get incandescent signals. You could get things that kind of changed. I think they probably boiled away a little bit and then turned into black carbon and then were observed in the sp2 as black
A
carbon.
related question would be, you said that the morphology, particularly the chains of certain exactly how they collapse on themselves, will affect the optics. Will that also affect the spectral signature? Because often brown carbon is estimated by subtraction of the spectral dependence of the black carbon, and the remainder is brown carbon.
Yeah.
I wonder if the morphology could be twisting that around somehow.
That's a very interesting point. Thanks for making it. So the thing that I would say is that so there's certain things that have been seen. You know, you collapse the core and you're going to get more scattering. The connection to absorption is weaker, but it makes sense just from me theory. If we believe the me, and so the me theory was done in the Azores, there's a station there, Claudio Mazzoleni collected microscope slides of particles, and at that remote station, everything kind of actually was very well simulated by the shell and core model. But if we have a fractal particle, it's absorbing its volume, then we would expect an angstrom exponent, something like 1, where let's just call it kind of like very small black carbon absorption signature. And then as we collapse it into spheres, what we'd expect is that the shorter wavelengths would become shielded more quickly than the longer wavelengths. And so you would be cutting down on the short order absorption. And that's kind of the opposite of what's seen with these tar balls and brown carbon. So if anything, that would maybe accentuate the role of the tar balls and brown carbon, but I think it would probably be very slight since we see such dramatic increases in absorption at low wavelength. But thanks for making me think about it. You don't have to. Okay.
Any more questions? If not, let's thank again Shuka.